In this podcast, we're going to talk about the relationship between equilibrium and Gibbs free energy. Okay, so just a little reminders about Gibbs free energy. When delta G is negative, that means your reaction is thermodynamically favored. It should happen. If delta G is positive, it means it's probably not going to happen. It's not favored to happen. And delta G must be negative or thermodynamically favored, less than zero, however you want to look at it, for a reaction to proceed in a given direction. So for it to go towards completion, it has to have a negative delta G. All right, here is an equation that describes the relationship between delta G and K, the equilibrium constant. As you can see, there are two equations. The first one is the one you'll see on the formula sheet. The second one is just that first equation rearranged to solve for K instead of solving for delta G. A couple things to realize, okay? Delta G must be in joules per mole. R. This is not our typical R. Typically we use the 0.08206 R. This is a different R, so you've got to put in your little brain, you've got to use this R. It's got joules in it, so hopefully that'll help you remember that this is the R we have to use. Temperature must be in Kelvin, and of course KEQ, you had to use partial pressures or molar concentrations in order to get that value. All right, so that's good and fine and all. We've got this lovely equation now, some more equations to deal with. But what does this all actually help us with? Well, if you know your delta G value, you can estimate the value of your equilibrium constant, and you can also estimate what the equilibrium is going to look like. What is it going to be? Mostly reactants, mostly products? All right, so if you have a delta G value that is greater than 0, what that means is it's not thermodynamically favored, so it's not going to want to go towards completion at all. So it's going to be very reactant favored, and we know that reactant favored things have a KEQ that is very small, so less than 1. All right, now if it's a super big delta G, like larger than positive 20 kilojoules, then what that's telling us is that this is a reaction that is very, very, very unlikely to go towards completion at all. So basically, it's not going to react. You're going to have all reactants, which means your KEQ is going to be super, super, super tiny. All right, now if you have a negative delta G, that tells you it's thermodynamically favored, so it's definitely going to go towards completion. You're going to make some products, and your KEQ is going to be a bigger than 1 number. If you have a very, very negative delta G, like negative 20 kilojoules, that tells you that this is something that goes towards completion as much as it can. So there's all products pretty much, no reactants, and you have a super, super large KEQ value. All right, now here's an example. So in this example, we're given the delta H value and the delta S value, and then we're asked to decide which of the descriptions do we think is going to be accurate for the system at equilibrium. So basically what we've got is values that we can use to get to delta G, right? So if you'll remember from our thermo unit, this is our delta G equation, except for I just screwed it up and I put a T there. Rotate, there we go. All right, so delta H minus T delta S. Okay, so if I plug this in, I'm going to go ahead and just make it joules. So joules-wise, it would be, let's see, making that to joules, you'd move it 3 spots. So negative 20,000 minus, we don't really know the T. I'm going to use 298 because that is a, it's kind of like room temperature. 273 is 0 Celsius, so 298 is like room temperature. All right, and then plugging in our negative 100 over here. All right, so basically what you end up with once you solve all of that is you end up with a positive 9,800 joules, which is kilojoule land is 9.8 kilojoules.
Okay.
All right, and with that delta G value, we know that this is going to be non-thermodynamically favored, so this is going to be mostly reactants. I wouldn't say all reactants because it's not that big, but mostly reactants. All right, let's look at this example. So we're given a reaction, a delta H value, a delta S value, and ask for the equilibrium constant at 298 Kelvin. All right, so we know that we have these values right here, these delta H's and delta S's. We can use those to find delta G, and then there is an equation we can use that relates delta G to K. So first things first, we need to find delta G. So we got to have our delta G equal delta H minus T delta S. Okay. We're going to put all these numbers in joules because that's what delta G needs to be when it goes into the equation to find the equilibrium constant. So I'm just going to go ahead and get everything to joules. So that'd be negative 198,000 minus, and then our T is 298, and our delta S is negative 188. All right, so do a little math, and that gives us a delta G of negative 141,976 joules. Okay, so now we can use our equation that relates K and delta G. All right, so we need to solve for our K. So K is equal to E raised to the negative delta G divided by RT. Okay, so here we go. Let's plug in all our stuff. So I've got E raised to the negative delta G is going to give us a positive 141,976. That's some crappy writing there, y'all. Let me fix that. Okay, all right. So it's going to be positive 141,976 divided by R times T. R is the 8.314, and then T, I don't know why my iPad's not liking me, is 298. All right, so I need to solve for this huge fraction here before I even try to plug it in and raise E to that number. Okay, so we've got E raised to 57.3, which is, all right, and for KEQ, we get 7.81 times, that is definitely a times 10 to the 24th. All right, now that's a huge K, but if you look back over here, we have a very, very huge delta G as well, a very negative one. So this is like a reaction that goes completely to completion, virtually all products here. All right, and a last example. All right, given a reaction, here is our K value. Here's our temp. Find delta G. All right, so we know that delta G is equal to negative RT natural log of K. Let's see. So we've got negative 8.314. The temp was 400. And our K is 3.94 times 10 to the 4th. All right, and I forgot the natural log. So we got to natural log this n part, then multiply it by all of that to get our delta G. All right, and for delta G, we get negative 35,189 joules. All right, and this makes sense, right? We have a pretty large K value, not super large. And we have a pretty negative delta G value, not quite 42, but pretty big.